Okay, folks, welcome to chapter 6, which is nuclear fissions. Okay, and I will be explaining 6.1, the liquid drop model. But before that, before I can jump into the liquid drop model, okay, there are a couple of things that I have to explain, okay, as the preparation. As we know, okay, as we all know, fission occurs with heavy nucleus. Okay, so such as uranium-235. Okay, so heavy nucleus splits or break into two parts, okay, producing two particles. So here it is written two particles of comparable mass. So meaning that the mass of those two particles, okay, are comparable. Here means both are to some extent large. Okay, it is not like the alpha decay. Okay? When you have a nucleus producing alpha particle which is very small. Okay? So that is what meant by comparable mass. So both are big. Okay? Big. This one also big. Okay, and of course the mass of the product particle is less than the original mass. So let's say this is the nucleus that will undergo fission. Okay. So after fission, you get two particle, not actually particle, but in fission, it is better if we refer the product as as product nucleus. Okay, yes. Okay, so nucleus 1, let's say this is nucleus 1, this is nucleus number 2. Okay, if you calculate the mass, okay, so the mass of that is 1, that is 2, that is supposed to be 3. So mass of 1 is actually greater than mass of combined mass number 2 and mass number 3. Okay, so there is loss of mass which is converted into energy. Okay, loss of mass, okay, converted to energy. Okay. So fission is the capture of a neutron. Okay. And for uranium-235, okay, to explain uranium-235, we will use the term thermal neutron. Okay. Later on you will see what is thermal neutron. Okay, so in general, fission is initiated by the capture of thermal neutron, okay, by heavy nucleus, and release about 200 mega electron volts. Okay, so this loss of mass converted to energy, which is on average approximately 200 mega electron volts. Okay, so fission is people like to use liquid drop, okay, to explain the fission of uranium, to explain the fission of uranium-235, and not necessarily limited to uranium-235. Okay, fission can be modeled using a liquid rock. Okay. So the uranium 235. Okay, let's say this is uranium 235. Okay, my eraser. Uranium 235. Okay, so it will split into nearly equal fragments. Okay, so this the entity name number 2 and entity name number 3, we call it fragments. Okay, so after absorb neutron, fission occur. So you get 2 fragments. Okay, and on average producing 200 mega electron volts. Okay, so the equation is uranium 235, okay, absorbing a neutron, okay, forming the so-called compound nucleus, which is uranium 235. Okay, so uranium, uranium uranium, sorry, not 235, uranium 236. Okay, because one neutron is added into the nucleus, so you get you produce uranium 236. Okay, so this is a compound nucleus and it is at an excited state, so it is not stable. Okay, which is why a star is given on top of the uranium 236. Okay, and this excited state lasts for a very short time. Okay, 10 to the minus 12 seconds. Okay, and it will split, okay, into X and Y. Here I use 2 and 3, but it refer to the same thing. Okay, so get nucleus X and Y, okay, which are called fission fragments. So so X and Y can be many combination. We will see that later. Okay, so so X and Y must comply to the principle of conservation of mass, energy, charge, and as well as the nucleon numbers. We see this. We have seen this in the previous chapter. Okay. Other than fission fragments, there are also, on average, okay, 2 to 3 neutrons are emitted. Okay, so what are exactly X and Y? So there are many reports, okay, for uranium 235. Okay, the fission fragment of uranium 235. Okay, let's Google it. Okay, so you can search uranium 235. I have my history here. Uranium 235 fission fragment. Okay, so go straight to the images. Okay, so this is what people used to represent X and Y. Okay, so I'm going to select maybe this one or this one. Okay, open in. Okay, so what you get? Okay, so what you will get? This kind of distribution. So if you plot x-axis as the mass number and y-axis as the percentage, okay, percentage. So this is what you will get. Focus on the line number red. Focus on the red line. Okay, not the light blue. Okay. So the red will get, you will get a peak. You will get two peaks. Okay, one peak is at about 90 to 100. Okay, mass number nucleus with mass number 90 to 100, and the second peak is 130 to 145. Okay, approximately. So those two peaks shows the most fragment that you will get when you fission uranium-235 with thermal neutron. Okay. Okay, I haven't explained what is thermal neutron. Okay. So actually thermal neutron is very low energy neutron. Okay. As opposed to thermal neutron, we will have later on a fast neutron. That is the high energy version of neutron. The name is fast neutron. Okay, so with thermal neutron, you get red, the broad red in color, and with fast neutron you get blue. So peak will eventually the same, okay, but the middle cleavage is higher with the fast neutron. Okay, so that's the fission yield of uranium-236. So it is called fission yield. Okay, so what you get from the fission of uranium-235. So this is what you get. So this is the dominant nucleus or fragment that you will get. Okay, here on the Y is the percentage. Yeah, on the X is the mass number. Okay, so you will get this shape. Okay? You cannot get other shape. That's nature. That's the beauty. That's the beauty of nature. So like I said just now, this is about 90, and this one 130 to 145 something. Okay, so precisely it is reported that it is barium 141 and krypton 92. Okay, so this one is krypton, that one is barium. Okay, so these fragments and neutron carries about 200 mega electron volts of kinetic energy. Okay, so most of the kinetic energy will go to barium and krypton. Okay, and only small portion of energy belongs to the neutron. So for the neutron, for the emitted neutron, okay, y-axis is the neutron energy. Okay, this is the percentage. Okay, y-axis is the percentage. So neutron produced from this fission. Okay, this energy and in MeV. Okay. So the dominant energy or most energy belong to the neutron is about 1 to 2 mega electron volt. Okay, until 9. Okay, so 9. So at after 9, so there is no, you cannot have a neutron with energy greater than 9 mega electron volts. Okay, so the most energy, the dominant or the dominant energy is about 1 mega electron volts. Okay, and still this is still considered as the fast neutron. Okay. So one mega electron volt is still considered as the fast neutron. It's not thermal neutron. So thermal neutron is far below here. Later on we will see about that. Okay, so you get energy from fission, okay, but most of the energy goes to barium and the krypton. Okay, another terminology. Okay, just now we had a fast neutron. Okay, so fast neutron is energy greater than 1 mega electron volts. Okay, so the dominant energy, the dominant neutron produced from fission of uranium-235 are fast neutrons. Okay, so fast neutron is greater than is neutron with energy greater than 1 mega electron volts. Okay. I don't remember whether I explained the fast and slow and thermal neutron in the previous chapter. Okay, forgive me if I forget this. But this is the definition. So fast electron is energy greater than 1 mega electron volts, and thermal neutron is energy very low energy, which is about 0.025 electron volts. Okay. So that it is not zero, but nearly equal to zero. Okay. The sense, that kind of sense. So fast neutron and thermal neutron. Okay, and then fissionable material. Okay, so fissionable material consists of isotopes that are capable of undergoing nuclear fission. Okay, by absorbing a fast neutron or thermal neutron. Okay, so any type of neutron that can cause fission reaction, okay, with the material. Okay, so that material is called fissionable material. Okay, so what materials are fissionable? They are uranium-238, thorium-232, uranium-235, uranium-233, plutonium-239, as well as plutonium-241. So doesn't matter the neutron is slow or fast, or the thermal neutron or fast neutron. Okay, so these isotopes will fission. Okay, and then we have second terminology is called fissile. Okay, fissile is fissionable material. Okay. Fissile material is fissionable material, but only fission by the thermal neutron. Okay, so if you have uranium-238, okay, you give it with thermal neutron. Okay, it will not fission. Okay, but if you give it fast neutron, it will fission. Okay, so only by thermal neutron. So uranium-235, uranium-233, plutonium-239, plutonium-241 are fissile material. So they only fission by thermal neutron. So even you have fast neutron, okay, which is the high energy neutron, you cannot you cannot make these fissile materials fission. Okay, and fertile. Okay, fertile. So opposite to fissile, it is fertile. Okay, fertile only fission by fast neutron. Okay, but fertile will be converted to fissile, okay, by absorbing thermal neutron. Okay, so fertile is fissionable only by the fast neutron. Okay, and if you expose it with if you hit it with thermal neutron, okay, it will not fission, but it will uh, will undergo a reaction, okay, which convert themselves into a fissile material. Okay, so it absorbs the thermal neutron and then it decays, and then the decay product is fissile. Okay, so that's terminology number 3. So back to the liquid drop model. So the breakup of uranium uranium nucleus can be compared to what happened to a drop of water when excess energy is added to it. So normal drop water is let's say like that. Okay, and if you give energy, okay, excess energy, it will vibrate. Okay, it will vibrate. Okay, and at some point it will split. So that's the liquid drop model. Okay, if you of water lah, of liquid. Okay, so the energy, will cause the drop to vibrate. Okay, and then elongate, okay, elongate and compress, okay, elongate and compress. Okay, so until the amplitude of vibration large enough to cause the drop to break. So this is the liquid drop model of water, and the same analogy is used for the fission of nucleus. Okay, so uranium. So let's say this is uranium-235. This is neutrons. Okay, captures the thermal neutron. Okay, remember uranium-235 fission only by thermal neutron. Okay, so this lead to the formation of uranium-236. Okay, uranium-236. So the absorption of slow neutron, okay, add excess energy into the uranium-236. Okay, other than change uranium-235 to uranium-236. Okay, the nucleus wise from uranium-235 change to nucleus to uranium-236. So that's the nucleus wise, but at the same time uranium-236 also gain excess energy. Okay, so it is unstable, it is at excited state. Okay, and this excess energy, it is called critical energy. Later we will see about the critical energy. Okay, so this initiate or this critical energy or this excess energy initiate the oscillation, okay, the elongation and compression. So perhaps looks like that lah. Okay, so elongation and compression. So at some point, okay, the uranium-236 is highly distorted, okay, and after a certain distance, force of repulsion between protons, okay, so after some distance, quite long distance, the electromagnetic repulsion force, okay, will act, okay, and that action cause the splits of the uranium-236. Okay, and at the same time, not exactly at the same time, but in a very quick moment, these fragments, it will emit 2 to 3 neutrons. Okay, so the same analogy used in the liquid drop model. So the most probable fission event correspond to the fission fragment with mass number 140 and 95. That's shown here. That's shown in equation 6.2. Please don't mind about the 7.2. Okay, in this equation. Okay, the fragments falls on the nutrient-rich side of the stability line. Okay, let's go back to the IAEA live chart. Okay, I have it open here. Okay, so if you this live chart. Okay, if you go, I'm just repeating what I told you in the previous video. So if you go to the right, okay, neutron number is increased, so means that x-axis is the neutron, and y-axis means that if you go upwards, your proton number increase. So y-axis is a z number, and black, okay, plot in black the stability line. Okay, the light blue is the neutron rich nuclides, green is proton rich nuclide. So if you click the drop down button here and you go for uranium-235 thermal cumulative fission yield, okay, if you go there, this is what you get. Okay, so this agree with the statement here. Okay, the most probable, okay, the dominant fission yield correspond to the mass number 140 and 95, about 140. Okay, and the second one, the first peak is A equal to 95. So this is same with the plot, same as this plot. Okay, this is mass number against the yield. Okay, but the IAEA use the live nuclide chart use different way or expression. Okay, so if we can check that. So A 140 and A 95. Okay, so if you go put your cursor over here, so it's about 95, right? So 95, 93, 95, okay, 94. So that's true. And then the second peak is about 136, 135, okay, 140, 138. Okay, and the rest, okay, the rest are fall below the line of below the line of stability, which I said just now is the neutron rich nuclides. Okay, so that is what meant by the statement here. Fragments that have large excess of neutrons are unstable. Okay, so instantaneously release 2 to 3 neutrons. So this is this is the origin of the neutron. Okay, that are produced after the fission. Okay, so instantaneously release 2 to 3 neutrons. Okay, and the remaining fragments are still rich in neutrons. Okay, and that one, and they decay to reach more stable nuclei through the beta minus decay. Okay, so so you get gamma ray. Okay, so I hope that's that explanation is satisfied enough for you to understand the process. Okay, then and next the critical energy. Okay, this is important. Okay, so energy required to split the excited compound nucleus into two is called critical energy. Okay, so at this state, so at this compound nucleus, okay, what is the critical energy? Okay, so when a proton is absorbed, okay, when a proton hits, okay, so the proton carries energy. Okay, proton carries energy as well as mass, its own mass. Okay, so its own mass change the uranium 235 to uranium 236. Okay, and as well as, so it carries its own mass as well as some energy. Okay, energy of the excited state compound nucleus, okay, is equal to so because the electron, the incident electron, the incident neutrons, sorry, carries energy. So the energy of the excited compound nucleus now is equal to kinetic energy of the incident neutron, okay, plus the binding energy of the last neutron, okay, due to its mass. So the neutron, this is uranium 235. So this neutron carries kinetic energy as well as mass. So when it's combined, okay, this is the neutron. Let's say this is the neutron. Okay, so now you get uranium 236. Okay, at excited state. So energy of the excited state compound nucleus now is equal to equal to the kinetic energy of the incident neutron and the binding energy of the last neutron. Okay, due to the mass. So this neutron, okay, contribute to the mass of the uranium 236. Okay, so now if the energy of the excited state compound nucleus is greater than the critical energy, the compound nucleus will split. So critical energy, okay, is the energy that if you can make if you can supply the energy greater than the critical energy of the nucleus will split. Okay. Okay, let's say okay, now let's do some calculation. Okay. We skip this table first. Okay, so let's think about the uranium-235. Okay, uranium-235 with thermal neutron. Okay, so the thermal neutron. Okay, the feature of thermal neutron is the energy is very low. Okay, so we can almost neglect the kinetic energy of the thermal neutron. Okay, so now the energy of the excited state compound nucleus is just the binding energy of the last neutron. Okay, so now so this is the mass of uranium-235. Okay, this is the mass uranium-235, which is 235.11704 atom AMU, or simply in unit. Okay, and we know mass of neutron is 1.00989 U. Okay, so if you total, you get 236.12602. Okay, so that's this is the excited state compound nucleus. Okay, so this is the mass of the excited state compound nucleus. Okay, because of the addition of the thermal neutron. Okay, and as opposed to this excited state compound nucleus, the uranium-235, the ground state uranium-236, sorry, not the 235, but the excited the ground state or the stable state uranium-236 is slightly less than this one, which is 236.11912 U. So the difference between this one and this one is about is 0.00690 U. Okay, and that equivalent to 6.4 mega electron volt. Okay, so this is now the binding energy of the last neutron. This is the binding energy of the last neutron, or this is the energy. Okay, this is the energy of the excited state compound nucleus. Okay, and the theoretical value of the critical energy of uranium-236, okay, the critical energy of uranium-236 is 5.3. Okay, and the energy of the excited state uranium-236 is now 6.4. Okay, from this calculation. So means that this is the excited state energy is greater than the critical energy, so fission will occur. So which is why even with thermal neutron, which I said we can neglect its kinetic energy, it is possible to make the uranium-235 fission. Okay, even though actually the splitting nucleus was uranium-236, but that was because of the absorption of thermal neutron with uranium-235. Okay, so this is theoretical critical energy. So with thermal neutron, you can, if you do the similar calculation here, okay, you can conclude that uranium-233 will be fission with thermal neutron. okay, as well as plutonium-239. So these guys are fissile material. Okay. Okay, but for thorium-232 or uranium-238, okay, uh, there are not fissile, they are fertile. Okay, like I said at the beginning. So you need so actually the so so with just the thermal neutron, okay, so the excited state compound nucleus cannot the energy is not exceed the critical energy, which is why you need to add more energy, okay, from the energy of the neutron. So you have to use the fast neutron. Okay, so you need to use fast neutron. Okay, for them to fissile. But don't forget that you convert. Okay, fission not occur with thermal neutron. So with let's say uranium-238, so fission will not occur with thermal neutron, but it will convert to fissile by absorbing the thermal neutron. Okay, so this table, okay, this table is additional information for you. I think if you understand the story here, you will appreciate the nuclear energy. So in the conventional nuclear plant, okay, in the conventional nuclear plant, okay, the fuel, okay, the fuel is uranium-235 and uranium-238. Okay, in nature, it's about if you mine uranium, okay, you will find that 0.3% is uranium-235 isotope, and the rest 99.7% is uranium-238. Okay. So this fraction is too low. Okay. This fraction is too low to put in the conventional nuclear reactor. Okay, to get sustainable chain reaction. Okay, which is why you need to increase the fraction of uranium-235, okay, to 3 to 5%. Okay, and this process is called enrichment. Okay. So for the conventional nuclear power plant, okay, so the conventional nuclear power plant, okay, the fuel is 3% uranium-235 and 97% uranium-238. Okay, so this enough. The 3% of uranium-235 is enough to create the sustainable fission reaction. Okay, so mixing with 97 uranium-238. So after typically like 18 months, okay, like or 2 years, okay, the uranium-235 will depleted. Okay, so will depleted, and at the same time, okay, this uranium-238 absorbs the thermal neutron. Okay, by the way, the conventional nuclear power plant is like water reactor, reactor. Okay, this is the current conventional nuclear power plant. Okay, is the light water reactor, which mean light water reactor means that it use water, it use H2O, okay, in order to moderate the neutron, so that you only the dominant the dominant population of neutron in the reactor is the thermal neutron. Okay. So like water, H2O is used so that the neutron population inside the reactor is the low energy neutron or the thermal neutron. Okay. And this thermal neutron will do the fission with the neutron, with the uranium-235. Okay, which is why it is called like water reactor. So after like typically 18 months, okay, 18 months to I don't remember, but typically 18 months, okay, uranium-235 will be depleted, okay, and at the same time, okay, because the large portion of the fuel is uranium-238. Okay, so the uranium-238, okay, during the fission of uranium-235, okay, uranium-238 actually absorbing thermal neutron, okay, becoming uranium-239, and then beta minus decay, becoming neptunium-239, which I said in the previous, in chapter 4. Neptunium is no longer available in nature but abundance in nuclear power plant. Okay, this is what the reaction was. Okay, and then that one, beta minus decay, producing uranium-239. Okay, so you get uranium-239 here. Lots of lots of plutonium, not uranium, plutonium-239 here. Okay, and still there are still a lot of uranium-238 remains in the spent fuel. Okay, or in the in the spent fuel. Okay, and at the same time, okay, if you continue, when you continue the plutonium, it will means that if the plutonium will further continue with the absorption of neutron, okay, becoming plutonium 240. Okay, so the plutonium again further the absorption of neutron, you are actually producing plutonium 241. Okay, this one. So rather than looking at rather than looking at this uranium-238, uranium-239, uranium-241, or plutonium-240 as waste, okay, you can actually fission. Okay, so if you reprocess the waste, the spent fuel, and extract plutonium-239, okay, plutonium-239 and uranium-241, okay, you can use them back in the light water reactor, okay, because they are fissile, they can fission by thermal neutron. Okay, you can put it back in light water reactor, okay, in the conventional nuclear power plant. Okay, and rather than using light water reactor, okay, to produce thermal neutron, okay, you can use fast reactor. Okay, so fast reactor is this is not yet become conventional. Okay, there are only few prototype fast reactor around the globe at the current moment. It is still prototype, but the concept of fast reactor is rather than thermal neutron, okay, it is utilizing fast neutron. Okay. So in the fast reactor technology, with the utilization of fast neutron, okay, you can use, okay, the balance of uranium-238 as well as the produced plutonium-240 to make them fission, okay, and harvest the energy. Okay. So okay. So if you use to the plutonium or the remaining to uranium-238 in a fast reactor, okay, you can actually guarantee the energy generation. Okay, it is expected that we can gain the energy, okay, from the fast reactor technology for approximately about 3,000 years ahead. Okay, so and then thorium. Okay, thorium is abundant in nature, okay, but the thorium reactor is still yet a prototype at the prototype scale. Okay, not yet conventionalized. Okay, but if this is realized, okay, we can expect that the thorium can support the energy production for another 1,500 years. Okay, so if you in the thorium reactor, okay, you actually begin with thorium. Okay, and by the way, thorium is also exists in nature. Okay, thorium-232. So thorium produce uranium-233, which is a fissile. So uranium-233 can be put back in the light water reactor. Okay. So with this technology, okay, it can support up to 1,500 years of energy generation. So in total, nuclear power, okay, can still support the human civilization for the next 4,500 years. Okay, that's a quite a promising idea, and I believe the idea will be realized in the near time. Okay, they are already prototype later, but not yet conventionalized. Okay, I think okay, let's continue for a few more slides. Okay, so some textbooks or some reference will conclude that the fission, I used to say 2 to 3 neutron, but some references conclude that it is 2.5 neutron per fission. Okay, and this product neutron will trigger another fission. Okay, so means that chain reaction would occur. Okay, so at the first stage, you get 2 to 3 neutron. Okay, and at the second stage, the two neutron, okay, will fission with two uranium, okay, and this will again produce two 3 neutron, okay, that one also 2 3 neutron, and this and at the third stage, I'm sorry, I hope you understand. I think you learned this before, at least in the secondary school. You has been exposed to this story. Okay, that give you 4, okay, for the third stage. Okay, so from 2 you gain 4, and then from 4 here you will gain 8. Here you will get 8 neutron. Okay, so it continue. Okay, so it will continue if you don't control this production of neutron. So the fission will become violent. Okay, the fission will become violent, and this is the principle of the nuclear bomb, uncontrolled fission reaction. But nuclear reactor, this production of neutron is controlled. Okay, and that is the under the subchapter chain reaction 6.2. Okay, so a nuclear reactor is a system designed to maintain self-sustained chain reaction. So the conventional nuclear power plant use uranium. Okay, so natural 0.7, remaining is 99.3. I told you in the previous slides. Okay, uranium-238 enable fission, okay, by thermal neutron. So it absorbs, producing neutronium and plutonium. Okay, so for this reason, at least 3 to 5% of the uranium-235 has to be enriched. Okay, so this one same explanation with these slides. This slide. Okay, so to achieve self-sustained generation, on average, 1 neutron emitted in uranium-235 must be captured by another uranium-235 nucleus. So the parameter for describing the level of reactor operation is called reproduction constant. It is defined as the average number of neutrons from each fission event that actually cause another fission. Okay. So K can have a maximum value of 2.5 in a fission of uranium. So it means that 1 uranium-235 produce on average 2.5 neutrons. It is the same meaning with this statement. Okay, so for self-sustained chain reaction, you need to maintain K equal to 1. Means that 1 neutron produced will cause 1 fission after that. Okay, so if K is low, so means that the chain reaction is reduced, is towards the reduction, and if K is greater than 1, it is towards the increment. Okay, and K less than 1 is called subcritical. K greater than 1 is called supercritical. Okay. The formulation K according to the nuclear reactor theory, K is not a simple formula, it's complex formula. If you are interested in the K, in the reproduction constant K, you can do some search. Okay, So that's all for this chapter. The rest for 6.3, I think you can read it by your own self. So that's for chapter 6, nuclear fissions. So thank you.